Good morning again. My pleasure to be here. I'm coming from Owens Corning Center of Science and Technology in Granville. The presentation this morning that I have is a collaborative effort. I've listed the contributors from our research center on the slide. I've covered a lot of subjects. I don't profess to be the expert in all of them, but I will give you an overview of the work that we've done at our research center. We have about 350 people there in the U.S. We have also technical service support in Europe and Asia Pacific. So we do a lot of work on building constructions, and I want to focus this morning on the envelope for residential buildings. I've identified 5 major subjects I'd like to cover, starting first with energy performance of the envelope, and get into the details of air infiltration, roof systems, water management, and acoustics. In terms of energy performance, I've identified 3 major driving forces. First one is energy codes, and I've spent a good deal of my professional career in the development of those. And we use economics, and those are driven by fuel prices and construction costs. We also have environmental goals as a driving force for energy improvement. So if we want to talk about energy codes, we need to have a little clarification on definitions. The basis for energy codes are heating degree days base 65, cooling degrees base 50, and moisture levels, moist, dry, and marine. And they also then, once you define the climate zone, we look at the thermal performance of the envelope in terms of its thermal resistance, or R value, thermal transmittance, U factor, and the solar heat gain. And this applies to fenestration, and that's a term for light transmitting devices. Well, not just a window, but it could be a glass block. It could be anything that transmits light. So if we look at heating degree days, what are they? Starting with, on the left, we have heating degrees base 65. Well, what does the base temperature refer to? And basically, it's the balance point of the house. And this was determined originally in the 1930s when people were delivering coal to homes, and they were looking for some weather measure to figure out when they needed to make the next coal delivery. They found that 65 degrees was a good correlation temperature. So that was used for many years, and it has been defaulted into our current codes today. So it's by no means the balance point of a house today. A good energy-efficient house will have a balance point of much lower temperature than that. But the way it's calculated is you look at the daily average temperature, and I've shown that as a dotted line on the left side for heating. And I show the 24 measurements for the day. And then the average is the dashed line, the black line. So in this example, I'm looking at 40 degrees as the average temperature. Our base is 65. So we take, and for that day, we have 25 heating degree days. So each day of the winter, we add those up, and that becomes the seasonal value. Well, 24 seems like a reasonable way to calculate the average, but it's entirely too sophisticated. So what's done is they take the maximum and minimum temperatures and average those to come up with the daily average temperature. And the reason they do that is that they don't have 24-hour measurements at all the weather stations. They have first-order stations which measure the hourly temperature, and there's about 1,000 of those. And they have second, third, and fourth-order weather stations, and they only measure max and min temperatures, so that's why they adopted that process. So that defines the heating side. On the cooling, it is used similar. You look at the daily average temperature and subtract that from the base. In this case, the codes are developed on a base of 50 degrees Fahrenheit. That came about in about the 1990s. So cooling wasn't a measure of metrics for many years in heating standards, or energy standards. And 50 degrees refers to the balance point of a commercial building. And what that means is that all the internal gains, the people, lights, and equipment, when it gets above about 50 degrees, you need to start cooling that space. So those are the 2 weather metrics for use in energy codes. But how does that compare to the long-term averages? So I looked at the historical data for Columbus. And on the top we see the heating degree days, and they're quite variable. And same way of the cooling degree days on the bottom. So for codes work, we use a long-term average. The first set of codes, we used a 30-year average of the weather data to set the codes. More recently, we've gone to 15-year weather data, and we're seeing a change in what the codes look like because of that. So if we look at a code today, it's broken down by climate zones. And these are defined by the heating and cooling degree days. And what are shown here are the 7 climate zones, starting down climate zone 1 in Miami, coming up to climate zones in Ohio, which is predominantly climate zone 5. But you see along the Ohio River, there's climate zone 4 that is available. That's what's in the codes today, but that's changing. We've just published the latest versions of the standards for 2016, and that's based on the new climate zone map. So that has changed. There's still the same number of climate zones, but where they are has shifted. And for Ohio, what we see is between the old or the current code, which has 9 counties along the Ohio River in climate zone 4. But in the new code, we're going to have 24 counties in climate zone 4, Franklin County being one of them that has changed. Climate zone 5 down to climate zone 4. So it's gotten warmer in Columbus. So that changes the criteria. So the way we represent that is a map showing heating degree days on the horizontal axis, cooling degree days on the vertical axis. And I plotted 4,000 plus stations in the U.S. And in the center of it are all of the locations for Ohio. And the little yellow triangle shows the original version of Columbus, and the dot shows the current version. And it just crosses the line at 5,400 heating degree days. That's what changed it from climate zone 5 down to climate zone 4. So if we look at the first energy code in the United States, it was published in 1975 following the 1973 energy oil embargo. And the goal was to eliminate the lowest 20% of the housing stock that was being built at the time. And that was developed by a committee within ASHRAE of 100 people, 10 subcommittees, 10 people on each subcommittee, and they used professional judgment to set that criteria. Where are we at today? Well, now we see we have various states having adopted different versions of energy codes. Recently, Ohio adopted the 2012 IEC Energy Code, and that became effective in January 1 of this year. But that's not the most recent code. The most recent is 2015. And what we see on the graph on the right is that there's a lag between publication of a code and when it gets adopted by a state or jurisdiction. So we see that the predominant adoption is still at 2009. We're seeing increases above that, but we also have the laggards. We have a couple of locations where they're using the 2009, and then we have about 10% of the housing starts are covered by no code at all. So there's still a lot of opportunity for improving energy performance just in code adoption. This has become a recent focus of the Department of Energy to encourage states to maintain current versions of energy codes. When we talk about the Criterion energy codes, one of the major variables are thermal resistance, and that's called the R value. And I listed some typical materials, starting with just a single sheet of glass. It has an R value of 0.1. An asphalt shingle is 0.4. A half-inch drywall is about 0.45. A half-inch oriented strand board is 0.6. Aluminum siding is 0.6. This next one is really important, and that'll come into play later. An 8-inch concrete block has an R value of about 1. Also, 8 inches solid concrete has an R value of about 1. So when you build your foundation, you're not getting a lot of thermal protection from the masonry units themselves. Carpet is 2. If you look at a double pane window, we're getting an R value of 3. 2x4 stud, which is a common construction material, is a little over 4. A 1-inch XPS insulation board is R5. A 2x6 stud is almost 7. Then you get into insulation, And depending on the density, a 3.5-inch thickness cavity can be 11, 13, or 15. A 6-inch cavity can be 19 or 21, and 12 inches can be an R38. So this kind of calibrates you on the values that appear in the energy codes themselves. So if we look at the 2015 residential code, it's broken down by these climate zones. And we have the 1 through 8 climate zones today. Going in the future, we'll have 9 climate zones. We're adding a new climate zone 0. It doesn't appear yet in the 2015 standard. But climate zone 0 is developed for international applications, and it focuses on locations centered around the equator. So there are no U.S. locations in climate zone 0. So that may not appear in future energy codes for U.S., but the work we do for international standards, that's very important. What we see is that the criteria for fenestration is listed in terms of U factors. And the U factor is just the reciprocal of the R value, and it's for the entire assembly. So you're looking at the total performance of a window unit. So that's just the glazing unit and the framing. So it's a composite metric. Similar U factor for skylights. Then we have the solar heat gain coefficient. And the values there start out at 0.25, and they go up to no requirement. The scale on that is 0 to 1. And 1 represents the solar heat gain through a single sheet of glass. So if you like to control your solar, you'd want to have a lower value than 1. So it looks like 0.25 in climate zone 1, which would be Miami, is a low value. We look at ceiling insulation R values. They start at 30 and go up to 49. Wood frame walls, they start at R13. And then you have options when you get to climate zone 3. You can put R20 in a 2x6 wall, or if you build a 2x4 wall, you can put R13 in the cavity and use R5 sheathing. So it gives you options on construction. Mass wall, you have insulation shown as 2 levels. The first one in climate zone 3 is an R3 or an R4, and it depends on where you put the insulation. The values on the left refer to insulation that is installed on the exterior of the wall, which would primarily be a foam insulation, rigid board. And the values on the right-hand side are cavity insulation if you're framing out that mass wall and insulating on the interior and adding drywall. Then we have floor insulation R values. Basement R values follow the same format as the mass walls. There's 2 values, one for inside, one for outside. Slab on grade, we talk about the R value and the depth of the insulation. And finally, for slabs, we look at both interior and exterior insulations. So that sets the minimum criteria to build an energy efficient house today to meet code. In terms of fenestration, what I've shown here is an example of the options that are available. I've shown 173 fenestration options. And then look at what happens by climate zone. The first one is climate zone 1, which is the yellow dot. And that is showing on the horizontal axis, a U value of 1, which there's no products there. But you also have to meet a U value or a solar heat gain coefficient of 0.25. So in order to meet that requirement, you'd have to actually pick a material that would have a U value on the order of 0.6 at best. So you're going to do better than what the code requires just to meet, because there's 2 criteria. We have similar trends like that in climate zones 2, 3, and 4. When we get to climate zones 5 through 8, we've got the black dot, which shows a solar heat gain factor of 1. Well, it says there's really no requirement when you get into cold climates to reduce the solar heat gain. But to meet the U factor, you're going to have a solar heat gain factor that's on the order of 0.6 or less. So the codes are set to not limit construction options, but to give you choices. So once you make those choices, what kind of performance do you get? So I've looked at 3 different locations. First one on the left is for Miami, and this is looking at the energy performance of a 5-foot window, and whether it's single, double, or triple glazing. And you can see that there's a tremendous impact due to orientation. So that makes the design of your house important in terms of where you place your windows. So there's a big energy consequence of that orientation selection. we look at the middle graph, this is for St. Louis. That's similar to what we would see here in Columbus. And you see now the introduction of both heating and cooling impacts. Again, orientation shows a big impact in terms of the solar energy. So orientation is also important in the center zones of the country. And then the third graph is for predominantly heating. This is Bismarck. So you see predominance of heating energy use and cooling energy use, but again, very sensitive to orientation. So that's very critical in the overall design of your house. One of the major driving forces in our work in developing energy codes are fuel prices. And what we see is over time, they have continually increased. But it kind of does this in steps. We start with looking in heating and cooling energies. They're relatively flat. Then they go through a transition period. They're relatively flat. They go through a transition period. And the overall trend is fuel prices are increasing, have been, and probably will continue to increase. And then we see this issue of gas prices. They peaked and have come down. So that's been due to fracking and other exploration activities in the U.S. has lowered our price for natural gas. But we account for that in the development of our codes and standards. Fundamentally, what we do is look at this, what we call the characteristic cost curve. So if we look at, starting on the left axis, is zero energy savings. And we would define that as not an uninsulated house, but one that would have met previous energy codes. And we want to do better than the existing codes, so we look at what's our projections for the future. We go through that and we look at items or points 2, and that's characterized as the minimum of the cost curve. We look at point 3, and that's where we've reached cost effectiveness of conventional installations. And to go from point 3 to point 4 is another step in terms of technology. It's primarily renewables. So in terms of developing codes, we look at what's optimum economically to set the criteria as item point 2. So what does that look like in terms of details? I've put together a simple example showing insulation, and this would be primarily blown insulation you might see in an attic, because you can have a continuous value from 0 to any level you want. But this process applies to any of the metrics in the codes and standards, whether it's insulation, fenestration, air infiltration control, HVAC equipment efficiencies. So any metric you can use on the horizontal axis. And what I'm showing here is there's going to be an increase in cost of that metric with increased performance. Combined with that is the performance itself in terms of the energy savings, and that's the second curve. And what we see here is this law of diminishing returns. So the more energy efficient you get, the less benefit you get from that. So those are the two primary drivers in terms of setting the codes. And these are the life cycle costs. So when we're looking at the energy costs, we're looking at not just the energy today, but we're projecting energy costs out in the future, 30 and 50 years ahead. And if you can do it with any confidence, I'd appreciate having that information, because it's always quite controversial. In terms of the first cost, we also look at the impact of assuming that it's being mortgaged, so there's interest rates to be concerned with for your mortgage, there's tax considerations. Those are all accounted for in that first cost curve. So these are the life cycle curves, and what we do is we take these two curves, we add them together, point by point. We come up with the green line, and that's the optimization curve we use to set the criteria. So what we see is that it reaches a minimum point, and we refer to that as the optimum. In this case, it is a value of like R21. So we do this calculation for each climate zone because it changes with weather. Yes?
What climate zone is this?
This is just an example. It was, I think it was done for Chicago. But when we're setting the codes and standards, we realize that optimum is may not, when you have discrete products, it may not be consistent with how it changes from one climate zone to the next. So this is where the committee uses their professional judgment. So we could have options on either side of that optimum. And I've shown an exaggerated view of point A and point B. And it may not be that far apart, but the point is that they both have the same life cycle cost. So from our perspective in setting the codes and standards, the end user should be neutral. Their life cycle cost is the same. The question is, how does that change from one climate zone to the next? Is there a progression that makes sense? So we go through and we set those values, and then in all the code work we do, we have to send that out for public review. We get comments, and we have to respond to those comments, and so we get proposals to change them one way or the other. So we have two driving forces here. If you're the builder, you want to minimize your first cost, so you'd pick point A. You know, he doesn't care about the utility costs, and that's somebody else's problem. If you're the homeowner, you might be considered about point B. I know that energy prices are going to increase, so I might want to spend more and have those advantages, not knowing with any certainty what the fuel prices are going to be. So that's the choices we make in setting the standards themselves. And in going through that process, we feel that we've designed the home. Now we're lending about the 80% of the homes that were normally built. So we're requiring that you're building a much better house today than you did in 1975 just to meet the minimum code. We affectionately refer to that minimum code as legally the worst building you can build. So it doesn't mean it's the best. So the third major driver are environmental goals for setting codes and standards. And the major driver for this has been what's referred to as the American Institute of Architects 2030 Challenge. And this was developed by Ed Mesria from AIA. And the goal is to have all buildings be net zero energy by the year 2030. And that has been a major driving force in the development of codes. Has been alignment, has been accepted by ASHRAE, AIA, USGBC, U.S. Conference of Mayors, and the state of Florida. So this is getting a lot of legs. I'll show you the impact of that in just a moment. So what does that mean? If we're looking to net zero energy, we can go down our cost curve. We get to the optimum, shown here on this blue curve. And for the red dot, I've shown the 2015 IEC criteria for a particular location. Once you go beyond that, it starts to get very expensive using code metrics to make that improvement. So what are the options? So what we look at is what has the energy savings over time been? Starting in 1975, we put this scale together for, on the vertical axis, 100 being the value of the standard in 1975. And standard didn't change for about 10 years. And then we saw minor improvements. And then in 2006, when AIA come up with the 2030 initiative, the Department of Energy got involved with ASHRAE, signed a memorandum of understanding saying DOE would provide technical support to ASHRAE if we would work towards this 2030 goal. So ASHRAE embarked on that, and you can start to see a major decline in terms of the energy use. And that has taken us down to the 2015, we're down, estimated that we're going to be around on this scale of 40. So we've saved a tremendous amount of energy with the impact of energy codes, but those only address part of the energy use of a house, and we refer to those as the regulated loads. And that would be the envelope, air infiltration, lighting, HVAC, and surface water heating. So what's left? How do we get from where we're at 40, how do we get down to this red dot at 2030, which is zero energy? Well, the first step is to look at what we call plug loads. And that's anything that you can plug into the electrical outlet. So it'd be refrigerator, ovens, microwaves, a whole list of put together. It may not be all inclusive, but one thing you can do is make those Energy Star selections, and that will help achieve energy performance. But they're not covered by the Energy Code. That's something that the homeowner has to do after they move into the house. So that'll take us down to some level. I don't know what it is yet, but to finish it off, we're going to have to go to renewables. And that's going to involve photovoltaics, wind energy, or passive solar designs. So those are the challenges confronting the codes and standards development. So what do we do in terms of specific construction? Looking at particular options, we have concerns in the codes and standards with thermal bridges. And these thermal bridge is a low thermal resistance path connecting two surfaces. On the left, what I've shown is a typical 2x4 wood frame wall. And we see that we put R13 in the cavity. We have the wood framing member as an R4. So collectively, those perform at about a composite value of R11. You add other construction to that, sheathing, siding, drywall, air film coefficients. You get an overall performance of 18.6 for that wood frame wall. Now you have an option. You could build it out of steel. And when I was first addressed this problem in about the year 2000, I got a call and said, well, that steel's so thin, I'm just going to ignore it and assume that I get the full R13 in the cavity. So I dug around in some of our research files and found some tests that we had done, and I was shocked at the performance that was realized. That the R13 wall, in conjunction with that steel, performs at about an R6. And I said, what's going on here? Was the test right? So I checked. Yes, it was correct. Did a little back of the envelope calculations and found out that the steel is a factor of 1,000 greater in terms of its heat transfer than the insulation. So it doesn't take very much steel to just create this huge thermal bridge for steel construction. So is that important? Well, if we look at how a house is built, we see a lot of wood, we can see a lot of steel. And that's a major difference in terms of the energy performance that's realized. Other thermal bridges to consider is when you install a window in a wall, where do you put it? Diagram on the left shows that it's installed on the exterior. You think, well, that'd be a good place to put it for drainage. But in terms of thermal performance, you'd want to install that in the same plane as the insulation to eliminate thermal shorts, condensation, sorts of problems as well. Slab edge insulation. You exterior insulate the wall above grade, and below grade you insulate the interior. You think you've added the insulation, but you created a tremendous thermal bridge, a short circuit. So the best solution is to have the exterior insulation run continuous. In order to do that, you have to provide some sort of protection of that insulation above grade. And a lot of people either don't insulate or they don't do the protection right, so that can be problematic as well. But there are solutions to that problem. Another problem is basement walls. Well, I'll insulate the basement wall up to the grade line, and I've covered 90% of the wall. That's took care of that problem. But wait a minute, I told you earlier that basement wall has an R value of 1. Well, that 1 means it's a tremendous heat conductor. So that insulation on the outside might as well not be there. It's doing virtually no benefit. The soil provides benefit. The insulation doesn't add anything to that. So you're bypassing all that insulation on the outside and the soil when you have that exposed above grade. Well, let's solve the problem. Let's go inside and insulate on the inside, but we don't need to do the whole wall. We'll just go halfway down. El wrongo. That vertical wall is R1. You're just bypassing all that insulation again. So those two things you don't want to do. You think you've done the job right, but you haven't. You created thermal bridges. Well, I showed you the impact of wood framing. So if you go to a typical construction site, which I did to take these pictures, and look at what's being done today. The amount of wood that's used is incredible. I mean, I was amazed at what I would refer to as excess. And there are procedures called advanced framing technologies that you can employ that give you the same structural performance, but not near the level of wood framing or these thermal bridges. And it exists in windows, it exists in doors, headers. No matter where I looked, there was just these multiple stud paths. So are there solutions to that? Of course. What I've shown here on the left is a corner detail that involves 4 studs. Makes it difficult to insulate and gives you thermal bypasses. On the right is a 2-stud corner. Now that requires drywall clips in order to hold the drywall, but that is a technique that can be used and gives you considerable thermal improvement. So you go out to look at the typical house with all the corner details. I didn't see any that satisfied what I would call good design. And it just continues. The problems are just everywhere I looked. Then I was, well, how does steel look? And the picture on the left is a stairwell. And what we see there looks like about 8 steel members. And I don't think the front head of the Queen Mary was that strong, but it's going to be a lot of steel, a lot of thermal short circuiting, very difficult to get energy performance in that construction. So what are some of the solutions? One is if we can look at eave construction, we have on the left a standard truss, and it comes down and the top cord sets on the bottom cord at the intersection of the wall. Now that compresses the insulation, and you install this red baffle bat to provide ventilation, but you're decreasing the thermal performance by having that compression. So the solution is referred to as a raised truss. So you build that up, you allow the insulation to essentially become full thickness, clear out the edge of the wall system, and you get the thermal performance that you would expect. So one solution I showed on the 2x4 walls was foam board sheathing. And you have options. You can buy a 1-inch foam board sheathing, or 1.5 inches, or 2 inches, or 3 inches. In terms of codes, we set a maximum of 3 inches because of just how do you install something thicker than that. Trying to drive a nail through more than 3 inches is a challenge. It could cost justify 4 inches, but they said you can't build it. So if you have a choice, you can buy a 1-inch board. You can get an R5 in one XPS type of material, or an R6 in the polyiso. Which one would you buy? Does it make a difference? Well, sure, the R6 is a better performer. I'll take that. Well, let's talk about that. In the rating of foam boards, the Federal Trade Commission has what they call Rule 460, and it requires all manufacturers to rate their products at 75 degrees mean temperature. So when you do that, the XPS on the left is shown at 75 to be an R value of 5, and the polyiso at a degree of 75 degrees is an R value of 6. But they're also temperature dependent. So in terms of the XPS, as it gets colder, its performance improves. In terms of the polyiso, the performance improves up to a point, and then you see this dramatic drop when the blowing agent starts to condense. So what does that mean in terms of application? So if we overlay those curves, and I show you the temperatures of Columbus, Ohio, what do they look like? So we see this is the distribution of temperatures, and below 50 degrees, about 43% of our temperatures are below 43 degrees. We see a tremendous drop-off in the polyiso. So you can go through and do an annual calculation and show that the R5, the red line, gives you overall annual performance better than the R6. So you need to keep in mind product performance, not just at rated conditions. Yes?
I have a home that's ICF insulated concrete form, just 10 inches. How do you compare the performance of insulated concrete form and structural insulated panel to the lumber and...
Well, you have to go through and do that comparison on a U value. And that's the other part of the standards is they list what I showed were the prescriptive requirements in terms of R values. They also list the performance factor in terms of U values. So if you meet that U value requirement, you're in compliance with any material, and that's why that option is provided in the codes. It gives you that flexibility. So you'd have to go through and do those calculations and make sure that you're in compliance with codes. Typically, that's not a problem with those types of constructions. That they're very energy efficient and have no problem in meeting codes. All right, second major item I want to talk about is air infiltration. And this is the flow of air from one side of the envelope to the other due to pressure and openings. And so how leaky is a typical house? Well, typically it will exchange its volume every 2 hours. But we're setting codes to be more stringent. So what's the energy penalty? Well, it's a function of climate, size, leakiness, and many more. It accounts for between 25 and 40% of the energy use of your house. So it's something that you need to consider. So how do you test that? With a blower door. So you pressurize your house and you take measurements, and then now the codes have set requirements. And for climate zones 3 through 8 requires 3 air changes at 50 Pascal. Well, what does that mean? Well, you have nearly a mile of joints in a house to connect. Which ones are the most important? So the infiltration, as I said, was for the IECC was 3 air changes at 50, and that 50 is comparable to like a 20-mile-an-hour wind. Now, you're not going to have that in your house on all surfaces, but it's a pressure test that we do, and we extrapolate those results down to 4 Pascal. That corresponds to about 4 miles per hour, and that's more representative of what you'd see in a house, and we refer to that as natural. So at 3 air changes 50, we're looking at about a quarter of an air change per hour to meet the code. So how do we get to that level? Owens Corning conducted a major research study to answer that question. And what we looked at is what are the options to get to that ceiling. So we started out looking at recessed lights. You got to seal those. Ducts connecting to your HVAC system. So we started to put together this list. We have the big bang, we have a medium set of options, and we have a third set which is near the top. So these are things that you can do. It tells you what the cost effectiveness is for each of those. Third item is roof systems, and we want to look at they got to breathe. You need to have ventilation in attics. You want them to defend your attic from moisture and snow, rain, and you want to seal them from drippage back into the space itself. So you have choices. In terms of asphalt shingles, you can have a 3-tab shingle, you can have laminate shingles of various weights, and hip and ridge shingles. So these gives you different levels of durability in terms of length of life. You also have sheathing requirements for the construction of a roof because you want to have these shingles firmly attached. And how do you do that? Well, there's codes on specifying how to install those correctly, how you install the nails to meet compliance, shown on the left, and 3 on the right don't comply. Ventilation is a major requirement for ventilation of roofs, and you do that by having air enter at the eaves, and you can have strips or little caps shown on the right to provide that ventilation. It goes into the attic space through those vent cavities that I showed earlier on the hip roof, and then exhaust near the top, and it can have ridge vents shown drawing on the right, or little louvered mechanical devices shown below the figure. We also want to have the proper wind resistance, and that changes by climate zone. So different tests are conducted on shingles, and different constructions are built for different areas of the country. So you need to keep that in mind in selection of the materials. You need to look at impact resistance, hail. You don't want that to destroy your roof. So those are tests we do to protect against impact resistance. Finally, shingles can only be applied if the roof pitch is greater than 2 and 12. And between 2 and 4 and 12, you need to have double underlayment application is required. And above 4 and 12, single layer is sufficient. You also need ice protection. I talked earlier about ice dams, and you want to, if those occur, you'd like to avoid them in the first place. With proper thermal design, you can avoid, certainly minimize those, but you want to have drip edge and underlayment installed so that if you do encounter that, the water's not coming back into your attic. So there's details on how that's supposed to be installed. And finally, we conduct tests on fire. So that's another important factor in terms of the design of a roof system. I'm looking at my time here, so I need to accelerate a little bit of my speech. Water management. What this drawing is showing is at the bottom, there's two little circles, which are the drain lines you should install in any foundation, whether it's slab, crawl space, or a full basement. And you need to be properly connected to something that will provide the drainage. Things you don't want to do. Take all that water that you collected from your roof, run it down your downspout, put a little elbow on the bottom and say, job is done. All you've done is dumped all that water at your foundation, and you wonder why you have a wet basement. So this, to me, is easily problem seen, but it needs to be corrected. But what you can do is install underground piping, but on the right, you actually need to connect it. Running it a little farther away from the house doesn't necessarily solve the problem either. So critical to pipe that water away from the house and connect all the joints that do that. But there will still be water beside the foundation, so what we recommend is a drainage system on the foundation applied on the exterior. And this is to take the water and have it conducted down to the drains at the bottom of the footers. The last area I wanted to just quickly talk about is acoustics. And the problem here is noise is unwanted sound. And the solution is to reduce or block that so that it's no longer bothersome. Now, this is something that most contractors don't design into houses. So if you're concerned about acoustics, you need to do this when you start with your contractor on day one, when you have a blank sheet of paper. Say, here's what I want to design. So what do you want to do acoustic treatments for? Well, you might have a home office you'd like to have isolated, or isolate your bedrooms, or you have a dedicated entertainment room or home theater. And where does the noise come from? Well, it can be exterior, it can be traffic, airplanes, trains, lawnmowers from your neighbors. It can be interior, entertainment systems, exhaust fans, and as we're looking at house designs today, they're becoming more open concept. So you see that the kitchen, the dining, and the family room is just one big space. There's no separation. So acoustically, they're all connected. So you want to watch your favorite sports game, and all of a sudden the exhaust fan comes on in the kitchen. You can't hear or see anything, or can't hear anything on your TV. So this is not going to solve that problem. If you need to have an entertainment room, it needs to be acoustically isolated. So what do you have to target? Everything. Ceilings, interior walls, exterior walls, floors, doors, ducts, plumbing, electrical boxes. You got to look at all of it because sound is transmitted the same way air infiltration is transmitted, through the air. So there's solutions to each one of these problems. In cavity insulation, you need to insulate all the ceilings, walls, and interior walls. So if you want to separate a bedroom from a room, you need to insulate that interior wall. Caulk all air paths. If you want to get good performance, double layers of gypsum. Doors need to be solid wood core, not empty core doors. And you don't want them undercut for your return air vent because that just allows all the noise to come through. So you want to have a ducted return, but you want that ducted return just to that one building or one room. You don't want to have a duct on one side or a vent on the same wall on the other side, a vent. It'll just allow the noise to come through. So it should be separated in terms of ducting. Same way with electrical outlets. You don't want those backed up from one room to the next. Ducts should be insulated. Windows should be sealed. Floors, you need blocking between rooms. And plumbing should be isolated. So the basic principles, you can absorb that energy, you can block it, you can have vibration breaks or isolators. And what we're showing here is the impact of open penetrations. And we look at the curves, and as you start from the top and come down, that's the amount of opening that you have. So the first one is 0.001. That's pretty tight. But you get down to 0.01, well, that's still pretty tight. You've lost some acoustic quality in that space you're trying to design. So it's very important to have all the penetrations well sealed. You can decouple the vibration path between rooms with resilient channels or double studs, multiple options. You can use cavity insulation, as again, insulate interior walls. And I mentioned earlier double drywall. Well, double drywall gives you some improvement, and some people think, well, if 2 is good, 4 is better. A little bit, well then 8 would even be better, but 16 would be ideal. Well, is your house going to support it? I don't think so. So there's a optimum design and how far you want to go with each of these features to achieve your end performance. Another thing to consider is flanking losses. You think, well, I've got my walls protected, but now my floor is continuous. I design my house, I build my floor, I set the partitions on top of that. That floor acts as a channel for the vibrations to occur from one room to the next. So there's designs you need to consider there. So all these designs are never addressed in a conventional home. So if you're doing acoustics, this is above and beyond normal. It's very focused. So just about running out of time, so I'll take any other questions that you have, if I haven't bored everybody to death yet. Yes.
Can we take a closer look at the infiltration, the various joints? Because you had them highlighted as most important to least important to reduce air infiltration.
Yes. All right, we start out with most important thing to do is recessed lights that you have in your ceiling. And duct boots, connecting the duct to the register, it needs to be well sealed. Then top plated drywall, a garage wall, and the band joist. Those are the things that you need to look at first. That was the biggest bang items. Next items would be outside corners, top plate, inside corners. I showed you some of those corner details. Those can just be quite problematic. Bottom plates to the slab and to subfloors. And then the last item was between 2 top plates. So when you're building the top plate, you usually put on 2 layers of, so you need to seal between those 2 plates. Wood framing to sheathing, and the vertical sheathing links on the outside, tape those. That's one of the last things that, if you've done everything else inside, that's one of the last things you need to look at. Answer your question? Okay. Yes?
Is there any new advancement in terms of moisture management in your assembly?
Absolutely. The requirement in codes is for walls is to install a vapor retarder on the interior. And with the addition of foam sheathing on the outside, you need to make sure that you're not trapping moisture, because it will get through eventually. So there's recommendations on the balance between the R value of insulation in the cavity and the R value of the sheathing, and those are climate sensitive. So it's not a single answer to.
I have a quick question.
Yes.
It's nice to have all this acoustic design to prevent all these noises. What if for a proper acoustic design, how much the actual cost will be introduced in the whole, an average whole?
I have no idea, because cost is going to be a function of how far you go, how big the room is, how many rooms you do. I don't have any numbers that I can quote with any confidence.
Thank you. Any other question? Are we off? No more questions.
Yes.
The new climate zone map?
Yes.
Franklin County climate zone 4.
Yes.
When does that take effect?
It takes in effect when the local jurisdiction or state adopts a code that has that in it. The first code that has it is the commercial code for buildings, which is Standard 90.1 2016. That was published with the new climate map in it. I think the 2018 IECC is being considered to have the new climate zone, but I don't know for sure whether it will or not.
So for residential, it doesn't look anytime soon that that'll be in effect?
No, not typically. I mean, I'm looking at states, and they're from anywhere from 3 to 7 years behind in adopting what's the current code that's been passed at the time. So it's not going to change today. All right, thank you.
Okay, if you have one more question, and then we can leave it.
One more question?
Let's put down a question to the, after all the morning speaker finished. Thank you.
Thank you.